Okay, y'all, we are back. I was having trouble logging in, man. I don't know what was going on. They had to confirm my email. I did it like 4 times. It was not letting me log in, but it's all good because we are back. We are live. We're back in full effect, y'all. So let me get on here, make sure my audio is coming in clean. Audio coming in clean. Yes, sir. Yes, sir. All right, the audio coming in clean. Now let me come over here and this is some mushroom with cacao powder in it, or it's mushroom cacao powder. So it's like reishi and cordyceps and lion's mane, turkey tail, chaga mushroom, cacao mix, cocoa, cacao. I don't even know which one is correct. However, let me get back on this. I was trying to play y'all some of my AI music in the background for just a moment to as an intermission, so I wouldn't have to start a new stream and do a part two. So let's just see if this is still gonna work. Make sure the audio is clear. Okay, it's coming in clear. We'll do the whole screen. Okay, well that's not good.
Older monitor, you can see the tiny little squares. Each of those has some number of bits. Did here over here. One, you know what decimal number this is? This is not a fun mathematical exercise. The spoiler is 4,036,991,106 is the decimal number that actually represents, as of present, the most popular emoji in the world. Does anyone want to hazard a guess what emoji this here number represents? Hearts? No, but it's actually this so-called face with tears of joy. So perhaps think about the frequency that you send that one. And even though it's obviously a
All right, we're
picture
back,
on the
y'all. We're
screen,
back.
sure, it actually is more like a font, because underneath the hood, it's indeed just a pattern of zeros and ones or a decimal number that the computer is storing. But the computer, be it Mac OS or Windows or iOS or Android, know to display that pattern as this here picture. But the pictures might look different depending on the hardware. Why? Because there's companies like Google and Microsoft and Meta and others that have their own artists on staff as employees, and those artists interpret the descriptions like face with tears of joy differently. So those of you with an Android phone actually see face with tears of joy looking a little something like this. And if you have Telegram, for instance, installed on your phone, it's even more animated than that. It's this here emoji using the same pattern of zeros and ones. So different artists render these here emoji in different ways, but all they are here are patterns. Now, for all of the other answers, save one that was shouted out a moment ago, this is a sort of cloud diagram of the most popular emoji as of a couple of years ago per Unicode, whereby the size of the emoji indicates its relative popularity. So heart, I did here over here, is indeed one of the most popular ones as well. Question? A really good question. Why do certain emoji not show up on one device or another? It depends on how recent the software is. Pretty much every year, the humans behind the Unicode Consortium release new emoji, which is to say they decide that this other pattern will represent this new emoji. This other pattern will represent this new emoji. And unless you update your phone, your laptop, your desktop to the very latest software, and the manufacturer of that device or software also updates by hiring an artist to draw those pictures in their own font, in their own style, you're going to see usually just like an empty black square, or maybe just like a black and white heart instead of something more colorful, really just placeholders, because it's as though you don't have the right font installed, or really you have an older version of that same font installed. But it's become sort of an annual tradition that new and more emoji are released every year, which is among the reasons why these updates contain more and more. Yeah. That is an amazing segue. How do you represent color in bytes? Well, you use RGB, which happens to be, by coincidence,
To use color in bytes, you use RGB. Okay.
Incidents the next slide. So let's again recap. We know how to represent letters. We know how to represent numbers. We can even represent emoji. But those emoji technically on the screen are, of course, composed of colors, like a whole bunch of yellow for that their smiley face. How do computers then, using only zeros and ones, represent colors? Well, by convention, they typically use a system that by an acronym is called RGB, red, green, blue. And this is to say that a computer, to represent a single dot on the screen, maybe this one, this one, this one, will allocate some number of bits or some number of bytes to represent the color of just that their dot, otherwise known as a pixel. You can actually see pixels on your phone or even on your TV or monitor. If you go really close, especially if it's an older monitor, you can see the tiny little squares. Each of those has some number of bits telling the device what color to use. In particular, these devices typically use 3 numbers in total, 3 bytes. So that is to say 24 bits per pixel. And they do this. If you were to represent a single dot on the screen using these 3 numbers, just by intent here, this is 72, 73, 33, which in the context of a text message, an email, a Google Doc, represents, of course, high textually. What if a computer uses that same pattern of zeros and ones, that is the same pattern of decimal digits, to represent the color on a screen, which is germane if you're opening an image using Photoshop. So using a different piece of software that knows about colors and images and not just text. Well, this would imply that you want that dot on the screen to have like a medium amount of red, a medium amount of green, and a little bit of blue. Why do I see medium and little? Well, again, if each of these numbers is using 8 bits or 1 byte, the highest we can count, as we discovered, was 255. So I'm kind of averaging here. So 72 out of 255 feels to me like a medium amount of red. 33 feels like relatively little blue. But if now the computer combines those wavelengths of light, so to speak, a medium amount of red, medium amount of green, a little bit of blue, what you get is the color code for a single dot. And does anyone want to guess what color roughly this represents?
Red, green, and blue, like a purple.
These 3 bytes. Not white, not purple, not brown. Yellow, in fact, is the answer. So it represents in a single pixel.
Somebody yelling at me. Pause this.
So roughly this shade here of yellow, which is to say if we look back at any of those emoji, which again are represented by patterns of zeros and ones, but you and I as humans perceive them as images on the screen, let me actually go ahead and zoom in further to one such sample emoji. And when you zoom in far enough, or you put the phone close enough to your face, you can actually see all of those little dots known as pixels, all of the little squares. And given that so many of these pixels are yellow, that is to say that that pattern of 3 bytes, 72, 73, 33, is used to represent this pixel. Another 3 identical bytes are used to represent this pixel, this one, and so forth. So now if you've taken digital photos on your phone or a camera, you're probably generally familiar from the internet and hardware today that a photograph is what, like 1 megabyte, 10 megabytes, depending on the resolution of it. Well, megabyte means millions of bytes. Where are all of these bytes inside of these photographs or these images you're taking or downloading? they correspond to every one of the single pixels on the screen. There's at least 3 bytes being used to represent every one of those dots. As an aside, bit of a white lie, because nowadays there's fancy compression software that can use fewer than that many bytes. But in general, that's where all of those bytes, those millions of bytes, are coming from.
So let me make sure I got that straight. Each pixel is a byte. You know, that's what I'm. Each pixel is each pixel is represented by 3 bits in color to make a pixel. Something like that. I need to fact check that because I don't know if that sounds right. In fact, this is not quite accurate. Let me explain how color pixel to be represented. In most modern computer systems, each pixel color is typically represented using 24 bits, not 3 bits. 8 bits for red, 8 bits for green, 8 bits for blue. This is commonly known as 24-bit color or true color and allows approximately 16.7 million different color combinations. There are other color depth formats too. 8-bit color uses a color palette of 2d6. A 3-bit color system would only allow 8 different colors, which was actually used in some very early computer systems, but extremely limited and not used in modern displays. So I'm trying to wrap my head around what he was saying. What were those numbers he used? 77. 77 red, 73 green, and 33 blue equal as far as color. Let's see if it. SUG RGB color swatch. It would look more like a gold to me, but this color creates an olive brown shade. Okay, 42, 41. Let's go back a little bit.
Why do I see medium and little? Well, again, if each of these numbers is using 8 bits or 1 byte, the highest we can count is
each number is using 8 bits. So he said 72.
as we discovered was 200.
Is each color using 8 bits or 1 byte? I'm trying to get a better understanding of this because I work with cameras and stuff like that. So just seeing the back end of how these things works with the pixels is interesting. Okay, let's see if I can get a better understanding now. Yes, each color channel, red, green, blue, uses 8 bits, which equals 1 byte. So when you see number 72, 73, 33, these are decimal values that can range from 0 to 255. Okay, okay. Because 2 times 8 equals 56 possible values. Or 2 to the 8th power equals 256 powers. Okay.
155. So I'm kind of averaging here. So 72 out of 255 feels to me like a medium amount of red. 33 feels like relatively little blue. But if now the computer combines those wavelengths of light, so to speak, a medium amount of red, medium amount of green, a little bit of blue, what you get is the color code for a single dot. And does anyone want to guess what color roughly this represents? These 3 bytes?
So those are 3 bytes.
Not white, not purple, not brown. Yellow, in fact, is the answer. So it represents in a single pixel roughly this shade here of yellow, which is to say if we look back at any of those emoji, which again are represented by patterns of zeros and ones, but you and I as humans perceive them as images on the screen, let me actually go ahead and zoom in further to one such sample emoji. And when you zoom in far enough or you put the phone close enough to your face, you can actually see all of those little dots.
So each color channel gets 1 byte or 8 bits. So a full pixel uses 3 bytes. A full pixel uses 3 bytes, 24-bit for color, because 8, 16, 24. The value ranges from 0 to 255 to determine how much of each primary color RGB to mix together.
Dots
That
known
makes
as
sense.
pixels, all of the little squares. And given that so many of these pixels are yellow, that is to say that that pattern of 3 bytes, 72,
Although when I looked up the color, it was more of an olive green, but
73, 33
whatever.
is used to represent this pixel. Another 3 identical bytes are used to represent this pixel, this one, and so forth. So now if you've taken digital photos on your phone or a camera, you're probably generally familiar from the internet and hardware today that a photograph is what, like 1 megabyte, 10 megabytes, depending on the resolution of it. Well, megabyte means millions of bytes. Where are
megabyte means millions of bytes.
Are all of these bytes inside of these photographs or these images you're taking or downloading? They correspond to every one of
Megabytes as it pertains to photos or images correspond to what?
Of the single pixels on the screen. There's at least hardware today that a photograph is what, like 1 megabyte, 10 megabytes, depending on the resolution of it. Well, megabyte means millions of bytes. Where are all of these bytes inside of these photographs or these images you're taking or downloading? They correspond to every one of the single pixels on the screen. There's at least
every one of the pixels on the screen. Okay, let's go.
3 bytes being used to represent every one of those dots. As an aside, bit of a white lie, because nowadays there's fancy compression software that can use fewer than that many bytes. But in general, that's where all of those bytes, those millions of bytes, are coming from. So how is that for an answer to how do we represent colors? Thank you. So if we agreed now that there's this way and perhaps others to represent colors, well, how do we represent not just images, but videos? Well, videos, you know, once upon a time, or movies were called motion pictures. So most pictures with motion. Why is that? Well, it's analogous to growing up. If you ever played with one of these picture books, and in fact, there's memes nowadays that have made these popular again, whereby you have a whole bunch of images on individual sheets of paper, and if you flip through them fast enough, your human mind and eyes perceive it as actual motion, even though you're just seeing image, 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 but it's so fast it looks like motion. That's all a video is on your screen. That's all a film is on your TV. It is not, in fact, continuous motion.
I used to do that, y'all. I used to make little flip books out of little notepads. Really, I don't got none right now with the sticky notes. Oh, here we go. I ain't got enough, but you would color each one of these, make a little stick man doing something. My brother was real good at it though. You do one of these right here, and like make a little stop motion thing.
It's maybe 30 frames or images per second, maybe 24 frames or images per second, which is to say we know how to represent numbers, we know how to represent letters, we know how to represent colors and thus images. Now we kind of get videos for free because it's just more of the same. Use more and more of those patterns. Why are videos so darn large? Why are they gigabytes to download? Billions of bytes? Because there's so many darn images.
Giga meaning billions. Okay. That's good to know. Gigabytes means billions of bytes.
30 some odd images per second in those kinds of videos. And maybe lastly, just to top off our multimedia, how could you represent sound? Maybe musicians in the room, how using only zeros and ones could you represent something as sonorous as music?
Frequency?
Something analog as digital, yeah. Yeah, so each number that we store in the computer could correspond to a certain frequency, which has a direct relationship to the sound or the pitch of a note. For instance, in the world of piano and many other instruments, you've got like your A, your B, your C. Maybe you have sharps and flats as well. We could just agree, like the ASCII people did years ago, to represent the musical note A, let's use this pattern. Musical note A sharp, let's use this pattern, and so forth. But maybe pitch alone or frequency alone is not enough. Maybe we need that number, but maybe a second number for the volume, the sort of digital equivalent of how hard are you hitting the key on the piano. Okay. Maybe a third number for how long are you holding the key down. Sustained. So maybe the pitch and the volume and the duration, kind of like RGB, we could use 3 bytes to represent every musical note in some piece. And if we wanted to keep track of what instrument should be played by the computer to sound that music, well, maybe that's just a 4th byte or something else as well. Which is to say, at the end of the day, all we have are these zeros and ones to throw at the problem. So for now, that's it crazy. For representing information. We've got our numbers, we've got our letters, we've got our colors and images, our videos, and now sound. Any questions on how computers then are representing, as promised, those inputs and outputs using just zeros and ones? Yeah, in the middle. Correct. So the computer is taking as input at the end of the day zeros and ones and is outputting zeros and ones. However, as we'll learn in this class, by writing software, by writing code that understands those zeros and ones, we will enjoy not just literally seeing zeros and ones. We will see A, B, C. We will see colors. We will see video. We will hear sounds, so long as we write the code to interpret those zeros and ones. And indeed, it's worth noting now that that same pattern I keep using for an example, 72, 73, 33. How does a computer know? Is that the message high? Is that the color yellow? Is it a dot in a video alone? Yeah. Just depends on the context. Simply put, if you're opening that pattern of zeros and ones with like Excel or a calculator program, odds are the software will interpret those 3 bytes as numbers, of course. If though you open that same pattern in a text messaging program, Google Docs, Microsoft Word, that same pattern will be interpreted as a sequence of letters. Instead, if you open Photoshop, that same pattern, you'll probably see a single dot that happens to be yellow. Conversely, once you yourself are a programmer or even better programmer, you will be able to write in code how you want the computer to treat these patterns of zeros and ones. You can essentially tell the computer, use this to store a number or a letter or a color or something else. That's the power the programmer themselves have at the end of the day. Other questions? Okay. I'm representing things with bits.
Okay.
No?
Ones and zeros running our whole
lastly
freaking...
then, in this middle of this black box, so to speak, is the sort of secret sauce that solves problems, that converts those inputs to outputs, those problems to solutions. So what is an algorithm? It's really just step-by-step instructions for solving some problem. And indeed, I think back to my own first time in CS50 where we learned the same from Professor Brian Kernighan. And as luck would have it, just had my 25th reunion where we pulled some video footage from 1996. And so we're actually fortunate to have the very first few minutes of CS50 over 25 years ago when I myself took it. But the lessons back then as today are fundamentally the same. And what's important indeed is to not only express yourself correctly, but precisely, as we'll explore today. This then is Professor Brian Kernighan, who years ago very memorably introduced us and my classmates to algorithms by actually in class shaving his beard. If we could dim the lights here for Brian.
The other thing that we're going to talk about in this class is the notion of an algorithm. An algorithm is a very precise description of how to do something.
Write that down, class. Let me write that down. All right. Algorithm. Because we hear all about these damn algorithms with these new social medias and stuff, man. What the hell is an algorithm? A precise description of how to do something. Precise meaning what? A sequence. Hold on, let me get right. Y'all. A sequence of operations. Parentheses, using a specified set of basic primitive operations. He got that in parentheses. Primitive operations. I wonder if that description has changed now. Like, I wonder if we Google that, it might be more worded for, like, you know, Instagram, YouTube, TikTok algorithm type. I mean, I guess it's the same thing, but I just think how they word it, how they may explain it might be a little bit different. A precise description of how to do something, precise sequence of operations.
And the operative word there is precise. Okay, it has to be very, 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 very precise. And the task that I'm going to do is that I'm going to trim my beard, which has gotten out of whack. And I brought a variety of things which one might use to trim beards with.
What the hell? My boy got some hedge clippers and some damn some pruning shears. Nah, my boy.
So suffice it to say, I don't have much of a beard, but I do have this here other technology known once upon a time as a phone book. And these phone books, of course, have lots of information in them.
Man, people probably don't even know what a phone book is. Some of these younger generations.
Happen to be storing numbers and letters in particular. For those unfamiliar, they are storing humans' names from A to Z here in English, and associated with everyone's name is a number. So even if you've never had occasion to physically use this kind of device, turns out it's pretty much equivalent to the contacts or the address book app on your iOS phone or your Android phone as well. Why? Because if you pull up your contacts, of course, you see some familiar names here, alphabetized by first name or last name. And if you click on any of those names,
Diddy Kong.
you reach the person you're presumably trying to call or text. Pictured here then is John Harvard's, whose number here is +1 949 468 2750, which you're welcome to call or text at your leisure. But here is John Harvard that's partway through the phone book digitally. Well, it turns out that physically in the phone book, we might use an algorithm, step-by-step instructions for finding John Harvard in pretty much the same way as iOS, Android, macOS, Windows, or other operating systems themselves use. So I could, when looking for John Harvard, first name starting with J, I could start at the beginning of the phone book and start looking page by page, by page for John Harvard. And if he's there, I can call. This is an algorithm. It's indeed step by step, but that was a bug. It's a few pages turned. But is this algorithm correct? Step by step, assuming I'm paying attention. So yes, like if John Harvard is in here, I will eventually find him once I get to the J section. Now, this is a little tedious. It's going to take like a while, a few dozen, few hundred pages. So maybe I could do things a little smarter from grade school, like 2, 4, 6, 8, 10, 12, 14, 16, and so forth, going twice as fast. Is that algorithm correct?
Yeah.
So no, but why? I could miss him, right? I could just get unlucky, really with 50-50 probability, because John Harvard could be sandwiched between 2 pages. Now, this isn't a complete loss, this algorithm. Maybe what I could do is, if I get past the J section to like K, I could double back at least 1 page, just to make sure I didn't miss John Harvard. So I can still go twice as fast, plus like an extra step just to make sure I didn't mess up. So the first algorithm might take as many pages as there are in the phone book. So if this phone book has 1,000 pages, in the worst case, if I'm not looking for John Harvard, but someone whose name starts with Z, might take me 1,000 pages to actually get there. Second algorithm, twice as fast literally. Might take me 500 plus 1 step to get there, because I'm going 2 at a time, so long as I indeed fix that bug. But what we used to do back in the day, and what your phone is doing today, albeit digitally, is going roughly to the middle of the phone book, looking down and realizing, oh, I'm accidentally in the M section, so halfway through the phone book. But what do I now know about John Harvard? Is he to the left or to the right?
What do you say, M? It's my last name. It's to the left.
So he's obviously to the left, because J comes before M. So what I can do literally, and what your computer does figuratively, is tear the problem in half, throw half of the problem away, leaving us now with the same fundamental problem, but it's half as big. So I've gone from 1,000 pages suddenly to 500 pages. And compare this to the other two, 1,000 pages, 999, 998, versus 1,000 pages, 998, 996, 994. That's still slow. I went from 1,000 to 500 in just 1 step of this algorithm. What do I do next? I go roughly to the middle here. Oh, I went a little too far. I'm in the E section now. So is John Harvard to the left or right now? So he's to the right. So I can, again, tear the problem in half, throw the left half away, knowing now that John Harvard must alphabetically be in here. And I can divide and divide and divide and conquer this problem again and again by using that heuristic of going left or going right. And I dare say if I do this correctly, I'll eventually be left with 1 single page on which John Harvard's number actually is, or maybe he's not in the phone book at all. So how many steps
Just wasted a phone book, my boy.
maximally might that third and final algorithm take? It's not 1,000. It's not even 500 or 501. How many times can you divide 1,000 pages in half again and again and again?
Shoot. 1,500, 250, 125, 75. No, it'd be 70. It'd be 62 and a half, right? 62, 120, 64 and a half, 48. I don't know how many.
Roughly.
12, 10.
9, 10, so well, typically 10 times, give or take. There's a bit of rounding there because it's not a perfect power of 2, but roughly 10 times. Like, that is fundamentally better than both of the 2 algorithms, because I go from 1,000 pages to 500 to 250 to 125 and so forth, literally having the problem again and again. So we can actually appreciate and see this even more so graphically, and this is among the things we'll do later in the term when we speak to not only writing correct code, but is your code well designed? Is it better than your previous code? Is it better than someone else's code? Is it better than some other product? If you have given more thought to the algorithms and the quality thereof, you can perhaps minimize the time required to solve problems, but no less correctly. So if we have a simple XY plot here, on the y-axis or vertical is the amount of time to solve in whatever unit of measure, seconds, pages, however you want to count. On the horizontal or x-axis is the size of the problem, measured in, for instance, numbers of pages. So this would mean 0 pages in the phone book. This would mean a lot of pages in the phone book. This would mean no time to solve. This would mean a lot of time to solve. What's the relationship then among those 3 algorithms? Well, the first one is essentially a straight line, a slope of 1. And if the phone book has n pages in it, we'll describe the slope here as essentially 1/1 for the algorithm with the first algorithm, turning page by page by page, which is to say, if we were to add one more page to the phone book next year, first algorithm is going to take one more step. But the second algorithm is definitely better. It's definitely faster, but it's still a straight line. So it's going to take roughly n/2 steps on average, because you only have to go through half of the phone book because you're going 2 pages at a time, instead of the whole phone book, in the worst case, if someone's name is Z, to go through every page in total. So if we actually compare these, let me just draw some dashed lines. Suppose that you have this many pages in the phone book. If you just draw this vertical white line here, it's going to take this much time in red using the first algorithm, but it's going to literally take half as much time in yellow for the second algorithm, because you're literally going 2 pages at once. But the third and final algorithm is a fundamentally different shape. It instead looks a little something like this.
Log 2n. Okay. That's interesting. That is interesting. Oh, you know what? I would have never guessed that so much math was involved in computer science. It's all good, though. Okay. Well, so okay, log 2n. I don't. What is log? You know what I'm saying? Logged. Is that to the second power? Big O notation. Please find log 2n. Any code which is log 2n can theoretically said to be. What is it? It's binary logarithm. In mathematics, the binary logarithm is the power to which the number 2 must be raised to obtain the value n. This is for any real number x. Okay.
It looks like it's flatter and flatter and flatter. It's always increasing. It never gets perfectly flat, but it grows so much more slowly as a function of phone book size. And for those who recall their logarithms, this would be described as log base 2 of n. And in
log base 2 of n. How would I put that into my notes? Let's see. Is that some calculus shit? I don't think I ever took calculus. N divided by 2. I guess I should use a lowercase n though.
In fact, that's where the math came from. Log base 2 of 1,000 is roughly 10 in total, even if you need a calculator to confirm as much. But this shape is fundamentally different. Why? Well, suppose that Cambridge, where we are, and Alston, the town across the street next year, combine their 2 phone books. And they go from 1,000 pages each to one phone book with 2,000 pages. The first algorithm is going to literally take twice as many steps or pages. Second algorithm is going to take half as many, or 50% more, because you're going 2 at a time. But the third algorithm is going to barely miss a beat. Why? Because if this is 1,000 pages here and 2,000 pages is over there, just inferring from the shape of the green line, it's not going to be much higher on the vertical axis than the other 2 were. So more specifically, if you have a 2,000-page phone book next year, how many more steps will it take you using that third and final algorithm?
2,000. It'd be one more step, because it goes from half of a 2,000 is 1,000. And if we was going to do half of 1,000, 500, 250, 125, whatever half of 125 is, we only doubled the phone book, so it should just be one more step.
Just one, because you'll divide and conquer a 2,000-page phone book into a 1,000-page phone book, and then you're back at the original story. And that's the sort of power of learning algorithms. That's the power of learning computer science and learning how to program, is to be able to navigate big data, so to speak, things the size of Google, things the size of artificial intelligence training data sets, using better and better, more clever algorithms that perform faster and therefore not only make the software more competitive, but also make it more usable and more favorable for people like you and me when using that software. So when it comes to implementing algorithms as programmers, as computer scientists, what you're really doing is taking these algorithms, which might be expressed in English conceptually as we just did, but really just translating them to code, be it C or C++ or Python or R or Ruby or any number of other languages that exist in the world. But for now, let's consider how we might implement that algorithm using something that's literally still English, but pseudocode, something that is
What the hell
still
is that?
correct, but precise and finite, as per Professor Kernahan's advice, which is to say use your own vernacular of English and just say what you mean, but very succinctly. There's no one way to write pseudocode. It's not some formal language. I'm just going to convert the steps I did intuitively to step-by-step instructions as follows. Step 1, what I did was pretty much pick up the phone book. Step 2, what I did was pretty much open to middle of phone book for the third algorithm. Step 3, look at page. Step 4, if person is on page, then step 5, call person. If that does not prove to be the case, step 6
is if, else, elif. I learned this already. Look, it's if, s. Dang, if, else, elif, I believe is this sort of function.
Else, if the person is earlier in the book, then open to the middle of the left half of the book, and then go back to line 3. Then, if the person is later in the book, open to the middle of the right half of the book, and again, go to line 3. Else, there's a fourth and final case. If the person, like John Harvard, is not on the page, is not earlier, is not later, what's the fourth scenario we'd best consider? He's just not there, else we should do something specific like quit. Now, as an aside, everyone in this room has probably had one of these stupid technical support issues where your phone or your laptop or your desktop computer just freeze all of a sudden, or maybe it spontaneously reboots for no reason. Odds are that's because not you, but some other human made a mistake. They probably wrote code working at Microsoft or Apple or Google or somewhere else, and they didn't actually anticipate that, oh, there could be a fourth scenario that could happen in the real world. But if there's no code that tells the computer what to do in that fourth and final scenario, who knows what the computer is going to do? It might by default reboot. It might by default freeze. That's just a hint of the bugs, the mistakes in software to come. But even though this is just one way to write this code, aka pseudocode, there are some salient characteristics that we'll use throughout today. One, there are these verbs, these actions, and henceforth, as aspiring computer scientists or programmers, we're going to start to call these by what more technical audience would. These are functions. Okay. A function is an action or a verb. It's like a bite-sized.
Functions are action or a verb, bite-size what?
Task that a computer can do for.
Bite-size task a computer can do
for you. Those then are functions in this here pseudocode. But there's other types of code in here. There are these things here, if, else, if, else, if, else. Those are examples of what we're going to start calling conditionals. These are sort of
conditionals. I like that one. That's the one. That seemed like the one. Conditionals. If, else, if, else, if, okay.
Proverbial forks in the road where maybe you go this way, maybe you go this way, but you decide which way to go based on a question. The questions that you ask are what we'll technically call Boolean expressions, named after mathematician Boole.
Wait, Okay, conditionals. Boolean expression. I'm just gonna write that down. Boolean expressions.
Boolean expression is a question with a yes or no answer.
Boolean expressions is a question with let's get it, y'all.
A true or false answer, a black or white answer, a 1 or 0 answer. There's two possibilities, and there's a hint of the binary underneath. A Boolean expression is going to tell you yes or no, you should go down that fork in the road. Notice what's important here is that indentation mattered as a result. Notice that on line 4, when I first asked if the person is on page, question mark, so to speak, I should only do line 5 per its indentation if the answer is yes or true. I should only open to the middle of the left half of the book and go back to line 3 if person is instead earlier in the book. So indentation in pseudocode and in many programming languages has logical significance. It tells you whether to do things or not. But there's another construct in here, go back to, which literally makes me go back to line 3, potentially again and again and again, creating some kind of cycle or what we'll typically call a loop instead. So
Loop function. Let's get that in there.
even in this relatively simple real-world algorithm, we have these 4 fundamental characteristics of most computer programs that we will write in this class, and you might write beyond this class, that we have some technical jargon now to describe them.
He said 4. What are they? Conditionals, Boolean, loop. What the fuck was the other one then?
But what's important to note is that line 8 and line 11, even though they're saying go back to line 3, you might think you're running the risk of what we'll call an infinite loop, where you...
Time out. I got to figure out what the fuck is the other one. What are the first 4 basic functions in code? However, you're specifically asking about Scratch, since you mentioned it's 50 day 0. The first 4 basic block functions typically learn are motion, look, sound, play, and events. Okay. The most 4 basic functions in programming that are typically introduced are input, output, processing, storage. Okay. Well, I was talking about what did I get? What did I write down? I typed in conditionals, booleans, and loops. Prof. Malin was talking about algorithms and finding a name in the phone book. Man, that's, with ChatGPT, bro, you can't lose, or even with Claude. Like, I can just, man, it's crazy. Okay, let's see what we got here. Chat. W Prof Malin, y'all. That is funny. Okay. Now it's your friend of fundamental control structures and programming that Prof Malin discusses using the phone book example. Here are those: sequence, selection, conditional, loops, boolean. The phone book example demonstrates these concepts well. Boolean is the name we're looking for. Yes or no. Conditional. If the name Mike, stop. If not, keep going. Loops. Keep checking names until you find the right one. Sequence. The order of steps you follow, like starting at the middle of the phone book for a binary search. Prof. Malin uses this example to show the basic structures can create an efficient algorithm, like how you wouldn't start at page one to look for a name starting with Z, but rather use the control structures to search more efficiently. So here we go. Just copy that. Boom.
Literally get stuck in a loop forever, which doesn't sound like a good thing if at some point you want to turn your computer off, even though it's still working. But these will not induce infinite loops. Why? What is happening in this particular algorithm every time we go back to line 3 that guarantees eventually we will stop going back to line 3?
You find a name.
Exactly. If the person is on the page, we will call them or we will quit. But more importantly, because we keep dividing and conquering the problem, in this case, having the phone book, eventually we're going to run out of phone book, in which case, indeed, John Harvard is either on that page or not, and we will call or we will quit instead. So we'll see in time. And in fact, allow me to promise, odds are at some point you will write code that seems to take control of the computer for you, where it's doing something, and it literally won't respond to you anymore. That's just going to be because of a mistake, a so-called bug that you yourself will invariably have added to your code accidentally, but we'll show you ways for terminating it or breaking out of those.
Okay, I see what they did there. Man, Harvard, I got to go to that school. I just got to pop up on them one time. Oh, my camera went out. My camera sure did go out. That's crazy, y'all. Camera overheated. I'm sitting here talking to y'all. Y'all can't even see me, but it's not necessary. I'm gonna let my computer, or I'm gonna let my camera cool off a little bit, but we still gonna get through this, y'all, because I'm out here learning Harvard type stuff. You feel me? I'm a Harvarian. Y'all. Shout out to Harvard, man, for the freebie.
Those conditions. And indeed, what we'll do in just a little bit after a break for today's lecture is explore not just these concepts, but some of the ways you can use them to solve real and very visual.
Whoa, functions, arguments, return values, variables. Whoa, my boy. You gotta slow down, man. You gotta slow down, Prof. Malin. Functions, conditionals, Boolean expression loops. Functions. Okay. So those are the 4. I thought they were functions. What did he call them? Okay. Well, let's just write those down. Functions are okay. So yeah, I did have all of them. I thought they were called functions. Functions, conditionals, Boolean loop function. Okay, so conditionals. Okay, let's see. So for this one, he says arguments, return, values, variables. You heard? Okay, all right. Check. Let me make sure I'm still live with the audio, though. We still live with the audio? Okay, cool. We live with the audio. Let's continue, y'all.
Visual and audio problems. But for now, let's at least connect it to something that's been all too germane in recent months, the past few years, namely artificial intelligence, which is a topic we'll come back to at the end of the course, too.
Good, because hopefully by the end of this, I get my bot up, y'all. That's all I'm trying to do. You heard me? Let me get this thing. Let me put this camera back on for a second. I'm trying to get this bot up, y'all. That's all I'm trying to do is get my bot up. Over here splashing. And stuff. All right. Get my ass into Harvard. How much does it cost to go to Harvard? Let me see. How much does Harvard 52 bands for tuition, 12 bands for room, 7 bands for board, 3 bands student services fees, $1,500 for student health fees, student health insurance plan, other fees $3,700, or student health insurance plan for 85 bands per year. However, it's very important to know Harvard has one of the most generous financial aid programs in the U.S. Does it now? What does that even mean? About 55% of Harvard students receive need-based scholarship aid. Families making less than $75,000 per year typically pay nothing. Families making $75,000, $150,000 typically pay between 0 to 10% of their annual income. 10% of my income to send my kid to college? Well, I guess it's 15 bands a year versus 85 is cool. If I'm making 150,000 and they say 10%, I mean I gotta pay 15,000 for them to get into school versus the total cost of attendance is being like 85. Financial aid packages are determined on a case-by-case basis considering family income. The actual cost for most students is significantly lower than the full price due to Harvard's extensive financial aid program. Can I still get up in there? Can I still get in Harvard at the age of 33? Can I still? Because I know I got to get accepted. Like, what is the, you feel me? What is the Harvard Extension School? Well, less common adult students can still apply. Sam misses process. Institutional students will need to submit a full SAT, ACT scores unless waived. This is often the best path for adult learners. You can start taking classes without formal admission. After completing 3 courses with good grades, B+ or higher, you can apply for a degree admission. More flexible with online and evening classes. You need a SAT, show recent academic achievement. Consider community college classes. Write strong essays, explain your personal growth and why you're ready now. Potentially get letters, recognition from recent instructors. So I got to go to community college first. Okay. That's crazy.
To give you a sense of like what the connection is with what everyone's been talking about in the world of AI and what it is we're going to spend the next few weeks building up to by writing code. If you were to try to implement something like a chat bot, for instance, that just answers questions and has a conversation with you, you could do that using pseudocode. And as we'll soon see, you can use C, Python, any number of other languages too. That pseudocode might look like this when implementing a chatbot. You could tell the chatbot if the student says hello to you, then say hello back. And the indentation, as per earlier, implies this is conditional. Else, if the student says goodbye to you, say goodbye to the student. Else, if the student asks you how you are, say you are well. So you can just enumerate question after question after question and just handle all of these conditional possibilities. But things kind of escalate quickly, especially with the tools of today like ChatGPT. Are we really going to have the wherewithal as programmers to write another conditional like else if the student asks why 111 in binary is 7 in decimal? Like this kind of hints at, oh my God, there's like an infinite number of things this human could ask the chatbot. Do we really have to write an infinite number of conditionals? Like that's just not possible. Like there's not enough time in the day, there's not enough lines of code available. Artificial intelligence surely needs to be able to figure some of this out instead. And so indeed, this is not how you implement AI, but rather how you implement an AI like a chatbot is you typically train it based on lots and lots of data. You give it lots of inputs, training data, and let it figure out what it should say in response to certain questions. And it boils down to a lot of probability, a lot of statistics, otherwise known now as large language models, which if we really peek under the hood, are actually typically implemented with what
neural networks
are called neural networks, inspired by the world of biology, whereby we humans have all of these neurons that transmit electrical signals such that my brain tells my hand to move this way, and this other way. And so what computer scientists have been doing over the past many years is implementing in software, using literally zeros and ones, graphs or networks, neural networks that look a little something like this, where each of the circles represents a neuron, each of the arrows represents a pathway between them, and provides as input to these networks huge amounts of data, like all of the internet, all of Wikipedia, all of the books that it might consume as input. And then the goal of this neural network, as per this single final neuron right here, is to produce an answer to a question. Maybe it's simple, like yes, no, or maybe it's something like the answer to the 111 question.
Distractions. Whew, hold on. Sorry, y'all, I'm getting distracted. Neurons. I'm at 106.19. Let's see if we can go back a little bit. Yeah, okay. So neural networks, each one of these are neurons. This is based off biology, he said. So artificial intelligence is code, but it's based off the human brain, which is interesting. I guess that's what they call it, artificial intelligence, huh? Let me write that down in my notes. So under the hood of LLMs is neural networks, which is based off the biology of the human brain. That is some interesting stuff, y'all. I'm not gonna lie. I can't cat to you. I ain't gonna lie, bro. That's some interesting stuff.
Number of conditionals. Like, that's just not possible. Like, there's not enough time in the day. There's not enough lines of code available. Artificial intelligence surely needs to be able to figure some of this out instead. And so indeed, this is not how you implement AI, but rather how you implement an AI like a chatbot is you typically train it based on lots and lots of data. You give it lots of inputs, training data, and let it figure out what it should say in response to certain questions. And it boils down to a lot of probability, a lot of statistics, otherwise known now as large language models, which if we really peek under the hood, are actually typically implemented with what are called neural networks, inspired by the world of biology, whereby we humans have all of these neurons that transmit electrical signals such that my brain tells my hand to move this way, and this other way. And so what computer scientists have been doing over the past many years is implementing in software, using literally zeros and ones, graphs or networks, neural networks that look a little something like this, where each of the circles represents a neuron, each of the arrows represents a pathway between them, and provides as input to these networks huge amounts of data, like all of the internet, all of Wikipedia, all of the books that it might consume as input. And then the goal of this neural network, as per this single final neuron right here, is to produce an answer to a question. Maybe it's simple, like yes, no, or maybe it's something like the answer to the 111 question, or how are you, or goodbye, or hello, or the like. And what these neural networks do is use statistics and probability and try to output the most probabilistically likely answer to this question that's been asked, and really just hope that it is correct. There's no programmer at OpenAI or Google or Microsoft that's trying to anticipate every one of these questions we might ask, not only in English, but in other languages as well. So you might be wondering why there's this like 8-foot duck on the stage. So the persona that CS50's own AI takes is in fact that of a rubber duck. Because
see, I talked about this in my other video. It's some weird Harvard shit right here. I don't know what the fuck they talking about this rubber duck, but they saying this rubber duck is it's a chatbot.
As it turns out in programming circles, and this is true long before CS50, it has often been recommended to students and aspiring programmers that you keep like literally a physical rubber duck on your desk. The idea being, in the absence of a friend, family member, colleague, TA, who could answer technical questions for you, if you're alone in your room in Mather at night, you can sort of talk to the duck maybe door closed, and ask the duck your questions, or more importantly, talk the duck through what confusion you're having. And the mere act of talking through the problem
Are you serious, y'all? Are you serious? I'm about to talk to this duck. I'm not talking to this duck, y'all. Let me order a rubber duck on Amazon real quick. All right. That's crazy. That is crazy, y'all. You gotta talk to this duck. Okay. Let's get this back out of here. My bad, y'all. I had to. Let me be serious. Okay. Oh dang, I gotta get to the gym, man. Ugh. That is insane, my peeps. I don't know what my boy talking about with this rubber duck shit, but hey man, that's a CS50 thing. Now I know. Rubber duck means you probably went to Harvard or you're a computer science major. Cool. Rubber duck. See, you just I'm in the know now. Not reasonable. Using AI-based software other than CS50 something. Do I have access to this duck? That's the real question. That is the real question, y'all. Let's see if I can find this duck. I need my CS50.ai duck. CS50.ai. Let's see if they're gonna give me access to this duck. CS50 adaptation of ChatGPT for students and teachers beta with support from Microsoft and OpenAI. Okay, log in. CS50. Which account is this pulling from? So hold on, let me make sure. Oh yeah, that's the right one. So let's go. Let's go. Let's see what we got. Uh-oh. I got my CS50.ai duck, y'all. I'm in the game, man. What the duck? I couldn't resist. I'm sorry. I'm sorry, y'all. Let me share my window with y'all. Not that one, this one. Let me get my lo-fi on for a second. Let me get my lo-fi on. Quack. I'm CS50 Duck Debugger, DDB. Not to be confused with the boy Daryl DDG. Pontiac made, my boy. An experimental AI for the rubber ducking. What's rubber ducking, you ask? Let's find the duck out. In software engineering, rubber ducking debugging or rubber ducking is a method debugging code by articulating the problem in a spoken or written natural language. The name is a reference to a story in the book, The Pragmatic Programmer, and the programmer should carry a rubber duck. Interesting. Muy interesante. Okay, y'all. Um, Quack. CS50's Duck Debugger, an experimental AI for rubber ducking. Quack, quack. My replies might not always be accurate, so always think critically and let me know if you think that I've erred. Conversation log, quack, quack. Ask a question. How do, whoa, how, dang, how do I type? Do I build an AI agent trading bot to trade crypto on chain and on chain autonomously and also fetch relevant data for sentiment and price action on chain data like wallet size and transactions. And what else I wanted to do? Execute buys and sells. Execute buys and sells from exchanges. And what else I wanted to do? I wanted to I also need a back testing feature. I also need a back testing feature. This ain't really debugging, but building an AI trading bot for crypto is a complex project that involves several steps. Here are some general guidelines to get you started. Data collection. Use APIs to exchange to fetch price data. Use web scraping or APIs to gather sentiment data from social media and news. Use blockchain explorers to gather on-chain data processing. Clean and pre-processed data. Store the data in a database for easy access. Model development. Develop machine learning models to predict price movements based on historical data. Use sentiment analysis to gauge market sentiment. Backtesting. Implement a backtesting framework to test your strategy on historical data. Use APIs to execute trades on exchanges. Implement risk management strategies to minimize losses. Set up a server to run your bot. Continuously monitor the bot's performance. Okay, this is a question I do have. How do I make trades on an exchange that does not have an API? That's the real question. If an exchange does not have an API, you might consider using web scraping to interact with the exchange's website. However, be aware that web scraping can be against the terms of service of many websites and can lead to your IP being banned for other legal use. Always check exchange policy before proceeding. For web scraping, you can use tools like Beautiful Soup, Selenium, and Python to automate interactions with the website. But remember, this approach is less reliable, more prone to breaking if the website changes layout or structure. Okay. That's interesting. Muy interesante. My camera done overheated, y'all. It's all good, though. It is all good, y'all. We just gonna chill here for a second. We just gonna chill, y'all. We relaxing. We just chilling, y'all. I gotta give you some damn. We're taking a quick intermission, y'all. Okay, y'all, we are back. We're back. I had to let my camera chill out. I had to take a break. Really want to encourage y'all to get some blue light blocking glasses for real. These blue light blocking glasses is the truth. Shout out to the blue light blockers. Check. Can y'all hear me? I think y'all can hear me. Entire screen. Let's get this popping. Check. Is my music playing? Oh, it sure is. Welcome back. We are here chilling. We're gonna power through this. Got about 50 more minutes left. We're gonna power through this. I was ducking with the rubber duck. I'm gonna build this. I will build this AI trading robot. Don't you guys worry. It's coming. It's gonna happen. I'm starting with CS50. Now there's other CS50 type shit, you know what I'm saying? This is EDX, the platform I'm using. As you can see, they have more related programs. CS50 AP, Computer Science Principles, CS50 Science, Computer Science for Mobile Apps, Computer Science for Artificial Intelligence, Computer Science for Python programming. So really, it's this one, and this one are the ones I'm going to be looking into. Is this one free? Needs verified certificate, enroll, self-paced, upgrade to be verified, upgrade augment your program journey to track and plan progress to 2 courses in the program. I'm already doing that. Enroll, self-paced, started 2018. Certificate status, spending courses, enroll now. March 31st, completed courses. Well, we're gonna do this one at a time. I'm gonna get this damn CS50 certificate, y'all. F to BS, man. I think this is all available for you online also, people. Let's not forget that, okay? Let us not forget that, ladies and gents. Okay? Let us not forget that we can tap into this information for free. You can take college, Harvard courses straight from your crib, straight from la casa. You heard? All right, straight from la casa. Straight from la casa. We just chilling, y'all. I ain't gonna lie. All right, let's power through. All right, power through this last 50 minutes. We're gonna enjoy it. Lock in.
Throughout the course, CS50.ai. It will also be embedded in the programming environment you'll soon meet, which is called Visual Studio Code, a cloud-based version thereof. The duck will live in that environment as well as on stage from time to time, which is to say, we'll not only talk about, but use throughout the course this thing known as AI. But this is ultimately code that we're going to start writing next week. And unfortunately, this code here is written in a language called C. This is essentially the program that I lost 2 points on, like some 25 plus years ago. And it does look admittedly cryptic. And that's why today what we'll focus on is not what this code looks like, nor the zeros and ones that code gets converted to so your computer can understand as input what you want it to do. We're going to focus on a much more visual incarnation of this, but I know thus far this has been a lot. So let's go ahead and take a 5-minute break here. And when we come back in 5, we'll do some actual programming. So see you in 5.
Dang, I done took my own 5-minute break.
All right.
It was longer than 5, but we good.
So it's now time to solve with actual code some actual problems, albeit in a fun and visual and audio way. But recall that where we left off was this. Like starting next week, you'll be writing code that ultimately looks like this. But thankfully, you will not be writing zeros and ones. And no normal person, myself included, can understand what all of these zeros and ones are at a glance. We could take out some paper pencil and probably figure it out very tediously. But this is exactly the point. Computers only understand this stuff. But what we as programmers will start writing today and beyond is code at a higher level. And indeed, this is going to be frequent within computers.
You know what? Shout out to the people who invented like coding. I was thinking about it the other day. Like somebody invented the code. Like, what was you on? Like, what was you on for real? Like, I can't even imagine like what you was thinking. Like, what if we had a language for computers? And then like hold on, y'all. Dennis Ritchie. He dead. American computer science who created the C program language in the Unix operating system with B language with a longtime colleague Ken Thompson. Who invented Python? Guido von Rossum. Came out in 91, February 20th. Is he still alive? My boy Guido van Rossum? He's 68 years old, y'all. So, like, what does he do? He works for Microsoft. Oh, he got his own GitHub repository. Wait, what the fuck? This dude, look at his website, y'all. If you don't get your coding ass and make a better website, my boy. Look at this website, man. This is so basic. The margins all pushed up to the edge, my guy. Like, oh my goodness. I can't believe I'm seeing this. I am the author of Python programming language. See also my resume and my publication list, a brief bio, writings, presentation, interviews, all about Python, pictures of me, my new blog, my old blog. He's on Twitter. You can send me an email for me to Guido. For me to Guido@python.org. I read everything sent there, but I receive too much email to respond to everything. You understand? I do not give talks or keynotes anymore, nor do I participate in podcasts or give interviews, etc. I'm sorry, but I receive too many such requests to decline them individually. Offering payment or trips to exotic locales just makes things worse. Sorry. Also prefer to see questions about how to use Python. Bug reports, GitHub user tracker, my name often poses difficulties for Americans. The Dutch G is a hard G pronounce like the CH Scottish or whatever. Well, he don't got on GitHub, or let me see. Man, what kind of shit do he be coding, man? That's what I be thinking. What do these people who be coding like this type of a code to like make them breakfast? So crazy. Okay. My fault. I got distracted, y'all. My fault. That's on me. That's on me. We're gonna lock in. We're gonna lock in.
Science, where there's different like levels of abstraction that we operate at. And the lowest level, the nittiest gritty, is like the zeros and ones the computer understand. Like that's it in this class for zeros and ones. Hopefully you at least have wrapped your mind around why zeros and ones can be used in triples and in as bytes to represent higher and higher numbers. But let's just now agree that computers can do that. Let's abstract away from that detail and focus on higher level languages than zeros and ones, namely a language like this. So this is an example of the very first programming language I learned back in the day, as per that homework, in a language called C. It's an older language, but it remains one of the most popular languages and omnipresent languages nowadays because it's incredibly fast and it's particularly good at making devices operate quickly. For us pedagogically, the value of C is not that you're probably
Pedagogically. What does pedagogically mean? What the fuck? Man. Pedagogically means the way that relates to a theory and methods of teaching. It is an adverb that is used to describe things that are related to teaching, such as lessons, plans, classrooms, designs, teaching. The reforms are pedagogically questionable. The proposal was considered pedagogically too harsh. It teaches pedagogical philosophies that students learn better when they work collaboratively in a way that relates to theory. Okay, I can see that. Pedagogically. Okay, continue, my boy.
In Silicon Valley and other such jobs going to be using C yourself that much, but because it's going to provide a conceptual foundation on top of which we introduce other languages like Python, which is newer and improved, so to speak, that gives you more and more functionality sort of for free out of the box by abstracting away some of the stuff we'll focus on in the coming days first. So at the end of the day, you should better understand languages like Python and JavaScript and SQL because of your underlying understanding of a language like C. But this is too much for the first day. Many of you will think that this is too much for the second week. But in fact, C is really only sort of scary looking because all of this darn punctuation and syntax, the semicolon, the parentheses, the double quotes, the curly braces and the like. And I concur, like this is intellectually uninteresting. And a lot of the challenges early on when learning programming is you just don't have the muscle memory like that I or some of the teaching fellows might for knowing what symbols should be where. But that's going to come with time and practice. I guarantee it. What we'll do for today, though, is just throw away all of that intellectually uninteresting detail and focus really on ideas. And some of you might be in your comfort zone here because if back in middle school you were playing with a programming language called Scratch, you were probably using at the time just to have fun in class or out of class, making games, animations, interactive art.
Never heard of it.
Probably didn't use it for, at least in middle school, was to consider and explore programming languages themselves. But what's wonderful about Scratch, which is this graphical programming language from down the street at MIT, where it was invented some years ago, is you can program not by using your keyboard per se, but by dragging and dropping puzzle pieces, otherwise known as blocks, that will snap together if it makes logical sense to do so. And what you won't have to deal with is parentheses and double quotes and semicolons and all of that, at least until next week. But the nice thing about Scratch is that after this week and after the so-called Problem Set 0, the first assignment in which you'll use Scratch, you'll have a mental model via which it will be easier to pick up all of the subsequent syntax as well. So let's see how we can start programming in Scratch by making the simplest of programs first. You can do this at scratch.mit.edu. You needn't do this now in the moment.
Too bad. I'm going to do it right now in the moment. He said, what? Scratch.mit.edu. Scratch.edu.mit. Oh man, I gotta debug. Scratch. What the fuck? Oh, MIT.edu. Oopsie. Just start that up. Start us up too.
Problem set 0 will walk you through all of these steps. But what I've done here is opened up at scratch.mit.edu precisely the default web page therein. This is after having clicked the Create button in Scratch, which is going to allow me to create my first program. But first, a tour of the user interface here and what is ultimately available to you. Well, within the Scratch environment, we'll see a few different regions of the screen. One, we have this palette of puzzle pieces at left. The blue ones relate to motion. The purple ones relate to looks. The pink ones relate to sound and so forth. So the color of the blocks just roughly categorizes what that block's purpose in life is. We're going to be able to use those puzzle pieces by dragging and dropping them from left to right. In the right here, in the middle of the screen, is where I'm going to write my actual programs. This is where I'll drag and drop these puzzle pieces, lock them together, and actually write my code. What am I going to be coding? Well, I'm going to be controlling one or more sprites. Much like in the world of games, if familiar, a sprite is like a character that you might see on the screen. The default character in the world of Scratch is, in fact, a cat that looks like this. And if, in this case, I have just one cat, I can then make that cat do things in his own little world at top right by making the cat move up, down, left, right, spinning around, or doing other things as well. But if you want to introduce a dog or a bird or any number of other custom characters, you just add more sprites, and they get their own place in that same world. As for how to think about movement in this world, it's actually pretty familiar, even though it gets a little numeric for a moment. If Scratch at the moment is in the middle of the screen, the cat is at 0, 0. If you think about x, y coordinates or latitude, longitude, if you move the cat all the way up, this would still be x equals 0, but it would be y 180. What's the 180? 180 pixels vertically, or dots on the screen. This is negative 180 pixels on the screen at the bottom. By contrast, if you go left and right, your x value might change, negative 240, but y is 0, or positive 240, and y is 0 as well. But most of the time, you won't need to know or care about what the pixel coordinates of the cat are. All you're generally going to care about, as the programmer most likely, is do you want the cat to go relatively up, down, left, or right? And let MIT figure out the mathematics of moving this thing around in most cases. All right. So let's go ahead and introduce the first of these programs by doing something quite simple, as we did in C there, but a little more simply by writing code as follows. I'm going to go back to scratch.mit.edu. I've already clicked, per before, the Create button. And if I click on the yellow category of blocks here at left, and I'll zoom in, we'll see a whole bunch of yellow puzzle pieces. And probably the most common one you will use to write code in Scratch for just this first week is literally when green flag clicked. Why? Well, if we go back over to the cat's world at top right, notice that above the cat's rectangular world, there's not only a green flag for starting, there's a red stop sign for stopping as well. So let's do this. Let me go ahead and click and drag when green flag clicked anywhere into the middle and let go. And now I'm going to go to looks, and it looks like there's a whole bunch of purple puzzle pieces here. I'm going to choose something simple like say hello, drag it, and notice if I get just close enough, it's going to want to magnetically snap together. So I'll just do that, and it does its thing. The fact that there's this white oval with text means that is an input to this say puzzle piece. I can literally then change what the input is if I want to more conventionally say hello, world, which in fact, according to lore, was the very first program written in C, and nowadays in most every language, including in Brian Kernighan's book. So hello world is generally the first program that most any programmer first writes. So that's it as programs go. Let me go ahead and zoom out here. Let me go over to the right and click the green flag, and somewhat excitingly, maybe underwhelmingly, we've now written a program that quite simply says hello world on the screen. Now let's make this a little more technical for just a moment. What is this here puzzle piece, as I keep calling it? It's actually a similar, it's an incarnation of one of the ideas from our pseudocode before.
Print.
What did we call those actions and verbs last time in my pseudocode?
Functions.
Functions, that's right. So these purple puzzle pieces here are indeed functions, and some functions, as we can see, take inputs like hello, comma, world. After all, how does Scratch know what to say? You have to provide the cat with input, which is to say functions can indeed take inputs like this. In this case, one input, but we'll see opportunities for passing in more input as well. What the cat is doing, though, visually on the screen here at top right, is what's generally called a side effect. Sometimes when you call a function, it does something visually. And in this case, you're seeing literally a cartoon speech bubble, hello world. That is the side effect of this function. So if we now want to map this to our world of inputs and outputs and see where this side effect is, this is the paradigm I proposed at the start of class that is computer science in a nutshell and will be the framework we use literally throughout the class, no matter how the languages in particular evolve. So what's the input to this particular program? Well, this white oval, hello world, is my input. The algorithm, step-by-step instructions for solving some problem, is implemented in code, this language called Scratch, by way of this purple puzzle piece. And the output of that function, given this input, is the side effect whereby the cat indeed says, hello world visually on the screen in that speech bubble. So the exact same paradigm with which we began today governs how exactly this cat here works. Well, let's actually go back to this program and make it a little more interesting than that. Let me go ahead and click the red stop sign. And let me actually use a different type of puzzle piece, another function that does something a little different. First, I'm going to get rid of the say block. So I'm going to not only pull it away, I'm going to drag it over anywhere it left and just let go, and it will delete itself automatically. Or I could right-click or control-click, and from a little menu, I could also explicitly say delete. And what I'm going to do now is under sensing, which is a light blue shade of puzzle piece. There's a whole bunch here, but I'm going to focus on this one. Ask something and wait. And the default text is what's your name, and that's fine. But because it's a white oval, that input can be manually changed by me if I wanted to change the question. I'm going to drag it over here. It's going to magnetically snap together. And I'm OK with that question. But what do I want to say with the answer? Well, let's go ahead and do this. I could go to looks again. I could grab another say block, let it snap in. And I could say something like, hello, comma, David. But this is going to be the first of many bugs that I make, intentionally or otherwise. Let me click the green flag. Scratch is now, just like in a web browser, prompting me for some input here. So let me go ahead and type in my name, David, enter, and voila, like it works. Hello, David. I'm kind of cheating, though, right? Because if I zoom out, stop, and play again, let me type in like Yulia's name here, enter, and it still says hello, comma, David. So that didn't really implement the idea that I wanted. All right, so how can I fix this? Well, it seems that this time I want more than a side effect. I want to use the value that the human types in. And for this, we need another feature of functions, which is that not only can they sometimes have side effects, something visually happens, some functions can hand you back a value, a so-called return value that will allow you to actually reuse whatever the human typed in. So a return value is something that gets virtually handed back to you, and you can store it in something called a variable, like X, Y, and Z in mathematics, and you can generally reuse it one or more times. So let me actually draw our attention then to, at left, not only the blue puzzle piece, ask what's your name and wait, but notice that there's a special puzzle piece below it, this blue oval called answer, and that represents what a computer scientist would call a return value. So MIT has kind of bundled it together side by side to make clear that one of those pieces relates to the other. What it means is that I can do this. I can drag this oval and use this oval as the input to the say function. Now notice it's not the same size, but it is the right shape, so that's OK. Scratch will sort of grow or shrink things to fit properly.
OK.
But this too isn't quite right. Let me go ahead and do this. Let me go ahead and stop that, click the green flag. I'll type in my name again, D-A-V-I-D, enter. And it's just kind of like weird or rude. Like I wanted a hello at least, and it just said David on the screen. OK, so I can fix that. Let me stop with the red stop sign. Let me just separate these temporarily, and I can leave it in the middle there, but they have no logical connection temporarily. Let me go back up to looks. Let me grab a say block, a second one, and let me go ahead and say, just to be grammatical, like hello, comma, space, and then I'll reconnect this here. So at the moment, it looks like what I want. I want a hello, comma, and then the return value printed out based on whatever the human typed in. So let me zoom out. Let me click the green flag. Again, what's your name? DAVID, and watch the cat's side effect. Enter. Still not greeting me properly. There's no hello. And if in case it was too fast, let's do it again. Green flag, DAVID, enter. It rudely just says my name, which is weird. What's the bug here, though? It's a little more subtle.
You got two commands that are the same thing.
Yeah, it's just too quickly going over the say command or the say function in this case. My Mac, your PC, your phone is just so darn fast. Both are happening, but too fast for my human eyes to even notice. So we can solve this in a number of ways. I could actually use a different puzzle piece altogether. In fact, MIT kind of anticipated this. Notice the first puzzle piece in purple is say hello for a specific number of seconds. And you can specify not just the message, but the number of seconds, ergo 2 inputs, otherwise now known as arguments to a function. An input to a function is just an argument now. And that would be a fix here. I could maybe a little more explicitly do this. I could go under events, scroll down a little bit, and sorry, under control in orange, I could grab a wait block and I could kind of insert it in the middle. And this might actually help. So I could click on the green flag, DAVID, enter, hello, David, and I could change the timing to be a little more natural. But what if I want the cat to just say, hello, comma, David, all in one breath, so to speak? Well, for that, I'm going to need to use a slightly different technique as follows. Let me go ahead and get rid of the wait. Let me get rid of the second say block and stop the cat with the stop sign. Let me go under operators here, and let me somewhat cleverly grab this, a join block at the bottom. By default, it's using apple and banana as placeholders, but those are white ovals, so I can change those. Let me drag this over the white oval for the say function and let go, and it will snap to fill. Let me go ahead here and type hello, comma, space instead of apple. And what should I do instead of banana? Yeah, so the answer return value, the return value. So let me go under sensing again. Let me just drag another copy of it. And you can use these again and again and again. They don't disappear. I want to drag answer over banana so that the second input to join is actually, if you will, the output of the ask block, like that. And it snaps to fit.
You know what, y'all? Let's go.
So now if I go ahead and click the green flag once more, DAVID, enter, now we have the sort of behavior aesthetically that I cared about. But beyond the aesthetics of this, the goal here really was to map it to, again, the same paradigm, which we'll see here. The algorithm and the output and the input for this example are as follows. The input to the say block was, quote unquote, what's your name? The function, of course, implementing that algorithm in code was the ask and wait block. The output, though, of the ask block, recall, is not some visual side effect. It is a return value called answer, like a variable, especially.
Return value, answer. Okay, now we're getting into the nitty gritty of it. Getting to the nittiest of grittiest. Let us resume.
Special variable like X, Y, and Z in math, but in this one, we generally in programming describe variables with actual words, not just letters. But this output of the say block, I kind of want to make room for it to pass it into the say block as a second argument. So let's do this. Let's take one step back and propose that now for the join block that I just used, it takes 2 inputs, hello, comma, space, and answer. The function in question is indeed the join block. The output of this had better be hello, comma, David. What do I want to do with the output of the join block? Well, let me clear the screen. Let me move this over, because now the output of the join block is going to instantly become the input to the say block, so that the output now in this multi-step process is the side effect of hello, David. So the fact that I nested these blocks on top of one another was very much deliberate. If I zoom in here, notice that hello and answer are on top of join. Join is on top of the say block. And if you think back to like high school math, this is like when you had parentheses and you had to do the things inside parentheses before the things outside parentheses. It's the same idea, but I'm just visually stacking them instead. But outputs can become inputs depending on what the function there expects. Let me pause here and see if there's any questions about not so much like what the cat is doing, but how the cat is doing this. Questions at hand. All right, well, let's make the cat more cat-like and do this. Let me throw away all the say block and just let go there. And let me introduce at bottom left a nice feature of Scratch whereby there's also these extensions that tend to use the cloud, the internet, to give you even more functionality. And in fact, I'm going to click on this extension up here, text-to-speech. And if I click on that, I suddenly get a whole new category of blocks at the bottom, text-to-speech. They happen to be green. But what's nice here is that I can actually now have the cat say something audibly. So let me drag the speak block here instead of the say block. I don't want it just say hello. Let me stop that. So let me go back under operators. Let me grab another join block because I threw the other one away. Let me change Apple to hello, comma, space again. Let me go to sensing. Let me drag answer to banana again. And now let me hit the green flag. And let me type in my name, David. And in a moment, I'll hit enter and...
Hello, David.
All right, it's not exactly cat-like, but it was synthesized. But it turns out under these text-to-speech blocks, there's some others. Set voice to alto, for instance, seems to be the default. But let's change this. So notice that some puzzle pieces don't just take white ovals. They might even have drop-down. So whoever created that puzzle piece decided in advance what the available choices are for that input per the drop-down. So I'm going to change it to squeak, which sound, or actually kitten sounds even more apt. Let me zoom out, click the green flag. Type my name, David, enter.
Meow, meow.
That's interesting. Wow. So it doesn't seem to matter what I type. So how about David Malin?
Meow, meow, meow.
So it seems to meow proportional to how long the phrase is that I typed in. It can get a little creepy quickly. Like if I change kitten to giant, let me go ahead and hit play, David, enter.
Hello, David.
So you can sort of... for very non-academic ways, like start to have fun with this, but just playing around with these various inputs and outputs. But let's actually make the cat do something more cat-like and indeed meow instead of saying any words at all. So let me throw all of that away. Let me go now under sound. Let me drag the play sound until done. And notice in the drop down here, by default, you just get the cat sound. You can record your own sounds. There's a whole library of dogs and birds and all sorts of sounds you can import into the program. I'll keep it simple with cat. And let me click the green flag. All right, so the cat meowed once. If I want the cat to meow again, I could do this. If I want the cat to meow a third time, I could again hit play. So this is kind of tedious. If to play this game, I have to keep clicking the button to keep the cat alive virtually in this way. So maybe I want this to happen again and again and again. Well, let me just do that. Let me sort of drag and drop, or I could right click or control click, and then a little menu would let me copy paste or duplicate blocks, but I'll just keep dragging and dropping. Let's do this. Cat's kind of hungry, unhappy. So like this like slow things down so it's adorable again. So let me go under control. Let me grab one of those wait 1 second and I'll plop this here. Another one, let me plop it here. Click play again. Cuter, less hungry, sure. But this program is now, I dare say, correct if my goal is to get the cat to meow 3 times. But now, even if you've never programmed before, critique this program. It is not well designed, even though it is correct. In other words, it could be better. How, might you think?
Well, you would have to add a function somewhere. When you press the green arrow, the green flag, it can meow. If there's no other inputs, meow again. After, if there's no inputs, wait 1 second, meow again.
Yeah. So using a loop. And why? Why are you encouraging me to use a loop even though it works as is? Yeah, so to summarize, it's just easier to use a loop because I could specify explicitly in one place how many times I want it to loop. And moreover, frankly, any time you are copying and pasting something in code or dragging the same thing again and again, odds are you're doing something foolish. Why? Because you're repeating yourself unnecessarily. And this is a bit extreme, but suppose I want to change this program later so that the cat pauses 2 seconds in between meows. Well, obviously, I can just go in here and do 2. But what if I forget? And suppose this program isn't like 5 or 6 puzzle pieces. Suppose it's 50 or 60 or 500 or 600. Eventually, I or a colleague I'm working with is going to screw up. They're going to change a value in one place, forget to change it in another. So why are you inviting the probability of making a mistake? Just simplify things so that you only have to change inputs in one place. So how can I do this? Let me zoom out. Let me throw most of this duplication away, leaving me with just the play and the wait function. Let me now, under control as well, grab one of these. I could, for instance, repeat as follows. Let me grab a repeat. I'm going to have to kind of move these in 2 parts. So I'm going to move this down. It's too small, but it will grow to fit the right shape. Then let me reattach it up here. Let me change the default 10 to a 3. And now I think I've done exactly what you were encouraging, which is simplify. And I click play now. Meow, and yeah, so still correct, but arguably better designed as a result. I can keep things simple and change things now in just one place, and it will continue to work. But this is getting a little tedious now, I claim. Like, why am I re-implementing the idea of meowing? Like, wouldn't MIT have been better to have just implemented a meow puzzle piece for us? Because the whole thing is themed around a cat. Why is there not a meow puzzle piece? Why do I need to go through all of this complexity to build that functionality? Well, what's nice about Scratch and what's nice about programming languages in general is you can generally invent your own puzzle pieces, your own functions, and then use and reuse them. So let me go ahead and do this. I'm going to go under my blocks in pink down here. I'm going to go ahead and click Make a Block. And I'm going to be prompted with this interface here. And I'm going to call this block literally meow, because apparently MIT forgot to implement it for us. And I'm just going to go ahead and immediately click OK. And what you'll see now is 2 things. One, on the screen, I've been given this placeholder pink piece that says define meow as follows. So anything I attach to the bottom of that define block is going to define the meaning of meowing. And at top left, notice what I have under my blocks. I now have a pink puzzle piece called meow that is a new function that will do whatever that other block of code tells the cat to do. So what do I want to do here? Well, I'm going to keep it simple for now. I'm going to move the play sound meow until done and wait 2 seconds, though. Let's change it back to 1 second to move things along. And now let me drag the meow puzzle piece over to my loop such that now what's it going to do? It's going to meow 3 times. And just to be dramatic, out of sight, out of mind, let me, for no technical reason, just drag this all the way to the bottom of the screen and then scroll back up just to make the point visually that now meowing exists. That is an implementation detail that we can abstract away, not caring how it exists, because I now know at a higher conceptual level, if I want to meow, I just use the meow puzzle piece. And I or someone else dealt with already how to implement meowing. So now let me go ahead and hit play. Okay, so same exact code, but arguably better design because I've now given myself reusable code. So I don't have to copy paste those several blocks. I can just use meow again and again. But let's make one refinement. Let me actually scroll down to where I did, in fact, implement this. Let me control click or right click on it. And let me edit the pink block that I created a moment ago because I want to practice what I've been preaching about inputs. So I don't want this function just to be called meow. I want this function to also take an input. And just for consistency with our use of n earlier, which in computer science generally means number, let me meow n times. And just so that this puzzle piece is even more programmer friendly, let me add just a textual label that has no technical significance other than to make this function sort of read left to right in a more English friendly way. Meow n times. Let me click OK. And now notice this thing at the bottom has changed such that it's not only called meow, there's explicit mention of n, which is a circle, which is exactly the variable shape that we saw earlier when it was called answer. This is not a return value, though. This is what, again, we're going to call an argument, an input to a function. So let me do this. I'm going to move this back up to the top so I can see everything.
Argument is an input into a function. Okay. Let's write that down. argument is a input into a function. Okay.
In one place. And I'm going to make one modification because my goal now is to make a new and improved version of meowing that actually takes into account how many times I want the cat to meow. So instead of using a loop in my own program under when green flag clicked, I'm going to detach this temporarily. I'm going to move this away. I'm going to move this code over here, and I'm going to reattach it here. So focusing for the moment on just the left, meow is now defined as repeating 3 times the following 2 functions, play sound and wait. But that's not quite right. I want to get rid of the 3. So what can I do? Because I created this input to the meow function myself a moment ago, I can actually drag a copy of it, overwrite, that is change the 3 to be generally an n. So now I have a function called meow that will meow any number of times. And what's nice now is my actual program that is governed by that green flag. I can type in 3, I can type in 10, I can type in 100, and it will just work. And henceforth, I can again dramatically sort of scroll this down so we don't know or care about it anymore. Now my program is a single line whereby this notion of meowing has been abstracted away by just defining my own function or custom block. Questions then about just this idea, this principle of creating your own functions to kind of hide implementation details. Once you've solved the problem, therefore, you don't want to have to think about that same problem ever again.
I like that.
That's the beauty of programming, typically.
That was
Questions on what here we just did?
okay.
No? All right, well, let's do this. Let's now make this a little more interactive in code. Let me go to this green flag. Let me scroll down and just throw all of this hard work away that we have copies on the course's website of all of these programs step by step if you want to review them in slower detail. Let's do this. Under control, turns out there's other ways to loop. There's this forever block that will just do something forever. So in the forever block, there's some place for some other code. And I'm going to move to the control section here and grab one of these. If block, so one of these conditionals. Let's plug that in here, and now notice if, and then there's this sort of trapezoid-like placeholder that's gonna probably fit what? The if is a conditional.
The input.
Forever is a loop. Say and so forth have been functions. What was the other key term we used?
Boolean.
So a Boolean expression. We need to put one of those yes, no, or true, false questions here. So what are those? Well, I've been using Scratch for some years, so I know under sensing, there's one of these shapes here, touching mouse pointer question mark. The question mark literally evokes the whole idea of a Boolean expression being yes, no. It's way too big to fit, but it is the right shape. So let me drag it, let go. It's going to grow to fill. And now let me go to sound. Let me grab that play sound meow until done and put it inside that conditional, such that what kind of program have I just implemented here, arguably? What will this program do when I click the green flag?
It's going to be...
Well, nothing at the moment. But I'm not touching the cat, so if I move the mouse pointer to the cat, again, it's kind of like implementing the idea of petting a cat, if you will, because I'm forever just waiting and waiting and waiting. Is the mouse pointer touching that sprite, touching that cat? And only if so, go ahead and play that sound meow until done. But now we can make things a little more interesting. Let me stop this. And let me do something actually completely different. Let me throw all this hard work away. Let me go under extensions. Let me go to video sensing, because lots of laptops, my own included, has a little webcam nowadays. Let me approve use of that there, and you can see me in the frame. And let me do this. Let me drag one of these when motion exceeds some measure. And through trial and error, I figured out that 50 tends to work well. Let me step out of frame here and program off to the side. And if I go to play sound meow until done, notice that this is an alternative to using when green flag clicked. This is a category of block that's constantly waiting for what we'll call an event. An event is just something that can happen on the screen, a click, a drag, a mouse movement, and so forth. So let me zoom out here. And now, if I can do this, here we go. No, too slow. Still too slow. Oh, wait, did I click play? Let's see. Try again. There we go. OK, 50 is a little too high, apparently. So let's make this a little gentler. 10. OK, well, there we go. There we go. Okay, so we've implemented now more physically the idea of actually responding to a cat, to petting a cat. So
Digitally.
okay. Oh, damn it. Okay. Okay, so this is a bug. Like now, this is MIT's fault. So it's not stopping in response to the red stop sign. So what do you do in doubt? Most extreme, you reboot. For now, I'm just going to close the window. Okay, so now we've seen all of those primitives that we saw in that pseudocode, but incarnated in this graphical programming language. And again, without parentheses and semicolons and double quotes and all that punctuation that we will introduce before long. But for now, we have the mechanisms in place where we can do some really interesting things. So in fact, I thought, in the spirit of sort of thinking back on olden times, thought I'd open up the very first program I wrote when I actually I was cross-registered in an MIT class and took a class that introduced aspiring teachers to Scratch. And I implemented this program here called Oscar Time, which was a game that used a childhood song that I was a fan of. And it allows you to sort of drag trash into a trash can. But to bring this to life, and perhaps in exchange for one stress ball, could get one brave volunteer who wants to come up and control this here keyboard. I saw your hand first. Come on up. Come on up. And you'll see, thanks to the team, we also have this amazing lamppost here, being on Quincy Street as we are. Do you want to introduce yourself to the group?
Hi, my name is Anna. I'm from Richmond, Virginia, and I'm in Weld.
Nice, Weld. All right, come on over. So here, Anna, you'll have a chance to play the very first game I wrote in Scratch, which admittedly is more complicated typically than we would expect of a student doing this for the very first time, as in problem set 0. But what I'm going to do is full screen this here. I'm going to click the green flag, and what you'll see on the screen are these instructions. Drag as much falling trash as you can to Oscar's trash can before his song ends. And here we go.
Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash.
Oh, there we go. Nice. So as Anna continues to play, let's kind of tease this apart a little bit. So one, there's some costumes on the stage. Like that lamppost is actually never going to move, but there's a couple of sprites. There's the trash can, which seems to be a character unto itself. There's this piece of trash that keeps coming back and back. That is a sprite. There's now this sneaker, which is another sprite. And in fact, notice that Oscar, of course, keeps popping up from his sprite once in a while. So Oscar seems to have multiple costumes. So I offer this as an example as you keep playing, if you would. Very good job so far. Yeah, this song goes on forever. This was a nightmare to implement, to listen to this all day long. But how do we implement the rest of this? Well, notice that the trash, every time she throws it into the trash can, does reappear somewhere different. So there's some kind of randomness involved. And indeed, Scratch will let you pick random numbers in a range. So maybe it could be negative 240, maybe it could be positive 240 at the 180 point on the top of the screen. So you can sort of randomly put things on the screen. There's apparently what kind of construct that makes the trash fall again and again. I think no one's listening to me. They're all just watching you. But what's making the trash fall from top to bottom? So it's actually some kind of loop, because there's a motion block inside of a forever loop probably that just keeps moving the trash 1 pixel, 1 pixel, 1 pixel, 1 pixel, 1 pixel, creating the illusion, therefore, of motion. And if we can crank the song a little bit more, you'll see that this is all synchronized now.
Oh, I love trash. Anything dirty or stingy or dusty. Anything ragged.
The song keeps going forever, seemingly. And now notice more and more sprites are appearing because they waited for... Here we go, climax.
Love trash.
All right, a big round of applause for Hannah. Nicely done. Okay, there you go. Here you go. All right. So this is an interminable song. And indeed, I spent like hours building that, and just listening to that song on loop was not the best way to program. Terrible. But the goal here is to really use it as just an intellectual exercise as to how that was implemented. And we won't do the entire thing in detail, because I will say back in the day when I was younger, I didn't necessarily write the cleanest code. And in fact, if we see inside this and we poke around the bottom of the screen here, you can see all of my different sprites. and the code is kind of complex. Like things just kind of escalated quickly, but I did not set out and write all of these programs all at once for each sprite. I pretty much took baby steps, so to speak. And so for instance, let me open up just a few sample building blocks here that speak to this, that are written in advance. So here's version 0. Computer scientists typically start counting at 0. And let me show you this example here that only has 2 sprites on the screen. We have Oscar the trash can, and we have the piece of trash. And now notice, what does Oscar do? Well, let me go ahead and zoom in on this script, as it's called. The program is a script. When the green flag is clicked, Oscar switches his costume to Oscar 1. That's his default costume where the lid is closed. Then Oscar does this forever. If Oscar is touching the mouse pointer, change the costume to Oscar 2. Otherwise, change it back to Oscar 1. So that whole idea of animation where Oscar's popping in and out is just like a quick costume change based on a loop inside of which is a conditional waiting for the cursor, like Anna did, to get near the trash can. Meanwhile, if we look at the piece of trash here, notice that the trash is actually not doing anything in this first version because I didn't even implement falling first. So let me hit the green flag. Nothing is happening in this very first version, but notice if I click on the trash and drag, as soon as I'm touching Oscar, there comes that trash can lid. And it was just the result of making this one program respond to that input. All right, what did I do next? Well, next, after taking that single baby step, I added one other feature. Let's see inside this version 1. Again, Oscar is behaving the exact same way, but notice this time, the trash is designed to do the following. First, I'm telling the program that the drag mode is draggable. That is, I want the trash to be movable when the user clicks on it. Then I tell the piece of trash to go to a random X location. X is the horizontal, so it's going somewhere between 0 and 240, but all the way at the top of the screen, 180. Then forever, the piece of trash just changes by -1. So it just moves down and down and down. And without looking at the second script yet, let me just hit play and notice, without even doing anything, and eventually, once there was lots of trash falling, like Anna was struggling to keep up with this, it's just moving 1 pixel at a time forever until, thankfully, MIT does stop things automatically if they hit the bottom, lest a 6-year-old get upset that all of a sudden their sprite is gone forever. So there is some special casing there. But what else is this trash doing? Let me zoom in here. The piece of trash, also when the green flag is clicked, is forever asking this question. If you are touching Oscar, then pick a new random location between 0 and 240 at +180 and go back to the top. So in other words, as soon as this piece of trash is dragged over to Oscar like this and I let go, it recreates itself at the top. It's just sort of teleporting to the top, and thus was born this feature. And I won't slog through all of the individual features here, but if we do just one more and see inside this one. So now let me go ahead and hit play. Notice at the top left of the screen, there's a score, currently 0. But now when I click the trash and let go, notice that the score is being incremented by 1. And this, in fact, is how Anna's your score kept going higher and higher and higher. Every time I noticed, oh, the trash is touching Oscar, let's not only teleport, let's also increment a variable. And we didn't see this before, but if I go to this Oscar scratch now, you'll see that it is exactly the same. But if I now go to the trash piece here, and we go to when green flag clicked, you'll see that I'm initializing a variable in orange called score to 0. But if we scroll down to the bottom, Oscar is also doing another thing in parallel at the same time. When the green flag is clicked, Oscar is forever checking, is the piece of trash touching Oscar? If so, change the score by 1, and then go to top, which is another location on that screen. So in other words, even though at a glance, something like Oscar time might look very complicated, and it did take me hours, the goal, especially with problems at 0, is not going to be to bite off all of that at once, but to take proverbial baby steps. Implement one tiny feature so that you feel like you're making progress, add another feature, another, and invariably you might run out of time and not get to the best version of your vision, but hopefully it'll be good, hopefully it'll be better, but you'll have these sort of mental milestones, hoping that you at least get to that point, because as you will soon discover, everything in the world of programming, unfortunately, takes longer than you might expect. That was true for me 25 years ago, and is still true today. Well, let me introduce one final set of examples here, this one written by one of your own predecessors, a former student. Let me go ahead and open up 3 baby steps, if you will, toward an end of implementing a game called Ivy's Hardest Game, whereby it's now more interactive, quite like Oscar time. So at top right here, notice, and I'll zoom in, we have this world that's initially very simple. 2 black lines, 2 walls, if you will, and a Harvard sprite in the middle. But when you click the green flag, notice that nothing happens initially except that the sprite jumps to the middle. But I can hit the up key, or the down key, or the left key, or the right key. But if I try to go too far, even though it's not the edge of the world, it's only touching that there black line, it's still going to stop as well. So intuitively, how could you implement that type of program? How could you get a sprite, from what we've seen, to respond to up, down, left, right, but actually move when I touch my arrow keys? What does it mean to move? Yeah.
Click, move to a new chord.
Exactly. So much like with representing information, at the end of the day, all we've got is zeros and ones. When it comes to algorithms, at the moment, all we have are functions and loops and conditionals and Boolean expressions and soon some more things too. But there's not all that much we have at our disposal. So let me zoom out from this and let me actually show you what the Harvard sprite is doing. It's doing this. When I go up to the green flag here, the Harvard sprite is going to 0, 0, so dead center in the middle. And then it's forever doing 2 things, listening for the keyboard and feeling for walls, left and right. Now, those are not puzzle pieces that come with Scratch. I created my own custom blocks, my own functions to implement those ideas. Let's not abstract away for now. Let's actually look at these features. And indeed, to your instincts at left here, what does it mean to listen for the keyboard? Well, if the up arrow key is pressed, change Y by 1, move up. If the down arrow key is pressed, change Y by -1. If the right arrow key is pressed, change X by 1. If the left arrow key is pressed, change X by -1. So take sort of all the magic out of moving up, down, left, right by just quantizing it as plus, minus, this, and that. It's all numbers indeed at the end of the day. But what else is it doing? Notice that it did indeed bounce off the wall. So my other custom function, which I chose feel for walls to kind of evoke this idea, it's asking 2 questions. If you're touching the left wall, then change X by 1. So bounce in the other direction. Else, if you're touching the right wall, bounce in the -1 direction. And so what are left wall and right wall? I mean, I kind of cheated. I just used 2 more sprites. These sprites are literally nothing except black lines. But because they exist, I can ask that question in my conditional saying, are you touching those other sprites? And I could have colored them any way I want. But this is enough if I zoom in to implement this idea of going up, down, left, and right and preventing the sprite from leaving that little world. All right, so if you'll agree that there's a way now to implement motion, up, down, left, right, let's go ahead and implement this idea by adding a rival into the mix, like a Yale sprite. And what the Yale sprite is going to do, if I click the green flag, is this. So Harvard at the moment is still going to be movable with the arrow keys, up, down, left, right. But Yale, for better or for worse, is just going to mindlessly bounce back and forth from left to right forever, it would seem. The operative word being forever. So how's that working? Well, let's look. Here's the Yale sprite at the bottom. Let's zoom in on its actual code here. The Yale sprite starts at 0, 0. It points in direction 90 degrees, which means left, right, essentially. And then it forever does this. If touching the left wall or touching the right wall, turn around 180 degrees. So I don't want the Yale sprite to just stop by moving it 1 pixel to bounce off slightly. I want it to wrap around and just keep going and going and going forever. And that's it. Everything else is the same. So one final flourish, let's add a more formidable adversary like MIT here, whereby if I zoom in and hit play, notice that if I move the Harvard sprite, MIT comes chasing me now. Now, how is this actually working? Yale is just kind of doing its thing, bouncing back and forth. Now MIT is really latched on to me, and it's following me up, down, left, right. So how is that logic now working? Well, again, it's probably doing something forever, because that's why it's continually doing it. Let's click on MIT. This, too, is pretty simple, even though it's a pretty fancy idea. Initially, the MIT sprite goes to a random position, but thereafter, it forever points toward the Harvard logo outline, which is just the long name that your predecessor or former student gave the name for that sprite. And then it moves 1 step, 1 step, 1 step. So suppose this were an actual game, and in games, like, things get harder and harder, the adversary moves faster and faster. How could we make MIT even faster by changing just one thing here?
Make it move 2.
Like, how do we level up? Change the 1 to like 2 pixels at a time, 2 steps at a time. So let's see that. Let's go ahead and zoom out. Let's hit play. And now notice that MIT is coming in much faster this time. All right, so it wasn't noticeably faster. Let's do this. Let's move 10 steps at a time. So 10 steps faster than originally. I mean, now notice it's kind of twitching back and forth in this way. Why? Well, probably if we worked out the math, probably the MIT sprite is touching the sprite and it's bouncing off of it. But then it's realizing, oh, I went too far. Let me move back. Wait a minute, I'm still touching it. Let me move down. So you can get into these perverse situations where there is actually a bug, be it logical or aesthetical. But in this case, we probably want to fix that. So 10 is probably too fast for this to work particularly well. But the final flourish here really is to show you the actual version of a game that one of your predecessors, a past classmate, actually implemented. Before thereafter, we will adjourn for cake in the transept, which is the CS50 tradition. But can we get one more final volunteer to come on up to play Ivy's hardest game? I'm seeing your hand most enthusiastically there. Yeah, come on down very happily. In just a moment, we will indeed adjourn, but the goal here now is going to be to navigate a maze that's a little more difficult than the last. Let's have you first, though, introduce yourselves to your classmates in front.
Oh, hi, y'all. I'm Eric. I'm from Philadelphia, and I'm also from Hollis Hall.
One person from Hollis. Nice. OK, welcome. All right, so Eric, go ahead and take the keyboard here. It, too, will be all about up, down, left, right as soon as you click the green flag. And if we can crank the music.
Can't touch this.
So notice the black walls are a little more involved than last time, but the goal is to get to the sprite all the way at right and just touch it, at which point you move to the next level. But the next level, of course, has Yale doing its thing back and forth, but you've made it to level 3. But now there's 2 Yale, so another sprite is in the mix that's randomly moving a little different in terms of direction. 3 Yales.
I told you, homeboy. Can't touch
Next level, MIT's in.
That's how we living, and you know, can't touch this. Look at my eyes.
Nice. The walls are now gone. Princeton's in the mix. Nice. 2 Princetons. Oh, okay, new life.
Hey, they about to flag me for this. Hold on. Okay. Okay, y'all. Thanks for tuning in with me. Thank you for tuning in. That was the first class of the CS50 Harvard computer science class. So, yeah. The Scratch, I might play around with Scratch for a little bit before I go on to the next one. And I can see it now. I can see it how playing with Scratch can really implement these functions and stuff. I'm gonna have to learn C apparently before I learn Python, which is I guess is good. So yeah, I ain't really got much to say, y'all. Y'all seen it. We've been going for 2 hours, supposed to do like an hour earlier. We made it through. This was kind of boring. I'm not boring, but it's probably boring to watch if you weren't tuned in from the beginning. But I'm just gonna keep doing it, one step at a time before I actually get into the coding. I'm gonna have my own AI agent. I'm gonna be doing whatever I can to learn computer science, do whatever I can to learn how to code this AI bot. And I'm still gonna be dropping my encouraging motivational videos. I know these two fields aren't really related, but really they are. If you can use you can really use motivation and encouragement in any field for real. So I just want y'all to understand that. Stay encouraged. Do what you gotta do. You know, try something new. This is me. I'm trying something new right now. And if y'all get to the end of this video, shout out to you. And shout out to Anime 3Ds, whoever he that was that tuned in for a little bit and said hi. You know what I'm saying? So what up, Anime 3Ds? And to the rest of y'all, what up, what up? Peace to all the rebels. I'm out.